This video is 3A, and Chapter 3 is dedicated to solving systems. So let's first talk a little bit about what a system is. A system is when you need to solve for multiple things at the same time. So typically when we solve an equation, we're solving for x, and it's just one thing. But rarely does that ever happen. In real life, a lot of times you have to find multiple things and they intertwine and work together, and you're trying to figure all 3, 2, or 4 things out at the same time. So here's the number one rule for solving systems. If you have one thing to solve, you need one equation. If there's 2 things to solve, you need 2 equations. 3 things to solve, 3 equations, and so forth. So ideally, or not ideally, but for sure, how many things you need to solve, that's how many bits of information that you can translate into equations that you need. And in this chapter, we're going to focus on several different ways to solve systems. Graphing, algebra systems, matrix systems, but really they all related to solving systems. So this first video, 3A, is really dedicated to stuff that we should know how to do already. Solving a system of equations where we have 2 variables and 2 variables only. So this should be a review of, our first year of algebra. Okay, so again, let's take a look here at objectives. So we have basically, we're going to cover graphing, substitution, and linear combination, i.e. called elimination. That's usually what I like to call it. All right, so the first thing is real simple. You're given 2 equations. We need to solve for x and y. Notice they're both in standard form, okay? So one way to do it is simply put on a graph. So notice with the first equation, I did the cover-up method. So, we could say, okay, let's put 0 in for x, it disappears, and y is equal to 8. And we could see that right there. And then we could say, okay, let's cover up the y's and put 0 in for y and solve, and x is equal to, put it in here, and x is equal to -4. And there's our other point. So the first line here, we're going to do in red. We have an intercept at -4 and an intercept at 8. So we draw our line. Then the second equation, notice I just translated to y equals mx plus b form, slope-intercept form, and we get an intercept at -2 and a slope of 3. And you literally just graph them, and the nice thing is they intersect at a nice point, -2, 4. So we can see this is the one point that is on both graphs at the same time. So it's one solution. Even though the solution is made up of 2 pieces, -2, 4, that's the input, that's the output. If we plug in -2, we get out 4 for both equations at the same time. So remember, this is one solution to the system. It's composed of 2 pieces. So not everything's always nice and simple where you have a nice clean point. So we'll show how to use a calculator in class, to get points that aren't exactly nice clean integers. Okay, let's take a look at the next thing. We have substitution. Now again, substitution is where we can get a single variable by itself. So when I look at this equation here, notice the y in either equation is by itself, meaning there's no coefficient in front. So let's look at the first equation in red here. To get y by itself, all I did was take the -2x, move it to the other side, and y is equivalent to this. So what we're doing is, okay, when we write the second equation here in blue, instead of writing y, I'm writing its equivalent, which is 2x plus 8. So you simply just plug it in, and now we have one equation with one variable. So notice in all systems, in order to solve them, you have to solve them piece by piece, one at a time. So notice we started with 2 variables and 2 equations. Your goal is to eliminate one of the variables one way or another, and then solve for one variable and one equation at a time. And that's with any system algebraically they're trying to solve. So notice we have just x's here, and we simply distribute, combine like terms, and get x equals -2. I'm going to take that -2, plug it back in. Now again, you could plug it into any equation because they both are going to share the same solution. So I'm going to plug it into this equation here because y is already isolated. So it's simply just evaluate -2 in for x. So we have 2 times our input, notice right here, plus 8, and y is equal to 4. So we have the point negative 2 comma 4. Now notice this is the exact same problem as the graph. Negative 2 comma 4. Notice the same equations. So I'm showing you the exact same system, just showing you a different way to solve it. Substitution. Okay. So again, this works when you can get one variable by itself pretty simply enough. Now the next system here, well actually let's look at substitution again. This system here, what I'm looking for in this example is what variable would make sense to get by itself. Well, right here to x because it has no coefficient in front. So I'm going to isolate the x by itself. I'll simply plug it into the other equation. Now we also have one equation, one variable, solve for y, plug it back in, solve for x, and our solution is 1 comma 1. Okay. So again, this is another example of substitution. And again, you can use any system you want. I'm trying to highlight here that substitution would make sense because we could easily get x by itself. Now, let's look at linear combination / elimination. For this to happen, you have to eliminate a variable. So you have to get two equations so when you put them together, the variables are opposite each other and equivalent size so they cancel each other out. So here, notice we want to get the x's to disappear. So to do that, I double the first equation. And if you double it, you'd multiply everything by 2. So we now, instead of x minus 2y equals 0, you multiply by 2 and you get 2x minus 4y equals 0. Same equation, just double it. Okay. I want these numbers to be the same, want to be positive and negative, so when you add them together, notice they go to 0. You can always add equations together. You're just combining two pieces together. So notice we do that, it goes to 0. We have negative 4y plus 1y, so negative 3y, and y is equal to 1. Now that you have 1, you have to plug it back into an equation. Now again, you could pick any equation you want. So in this example, I went ahead and picked the second equation. Just plug in y. Now again, you have to go through a little bit more algebra. So there is a little more algebra in the second half here, but notice our solution is still 2 comma 1. So again here, instead of getting a variable itself, we're looking to force a variable to cancel each other out. Let's take a look at our example. Now here we have to multiply both the top and bottom because notice we can't easily get rid of. So we have to think, what does 3 and 2 go into? 6. So make one positive 6, one negative 6, and multiply all the way through. So notice the 2 also gets multiplied by the 6, and the 3 also by the 4. The number's over here. Add them together. The x's drop out, 12's drop out, doesn't matter. Y is equal to 0. Take the 0, plug it back in. Again, you could pick any equation you want. You could simply plug it in the top equation, you get the same value. And again, at the point negative 2 comes 0, that is a solution to the system. It's the same point on both. Now again, on this one, could I graph it and they intersect at negative 2, 0? Definitely. Could I have, solve for x and get x by itself? Definitely. But notice you would have had fractions, so that would have been ugly. So elimination makes sense in this case. Now, let's take a look at scenarios. When you're graphing a system, you have one of 3 different types of answers. You either have 2 lines that intersect at a point, so you have one solution, x comma y. Sometimes you have lines that have the same slope, and obviously they don't intersect, so parallel. So that means no solution. So basically, where do the lines intersect? Never. They never do, so there's no solution. And then you have one line on top of one another. So let's imagine that these 2 lines were scooted together and they're literally overlapping each other. So where do they touch? Everywhere. So in that case, we say infinite number of solutions. And things we look for in algebraically is, okay, one answer appears, or we come up with a statement that doesn't make sense, never happens, no intersection, or a statement that is always true, which means there's always going to be an answer. So let's take a look at some scenarios where we see that. So in this case here, we went ahead and did elimination. And notice when you multiply the top equation by 4, the x's drop out, the y's drop out, and the number on the end drops out. So you end up with 0 equals 0. So when does this happen? Always, which means it's the same line. If you multiply this equation by a negative, you'll notice it's the exact same equation. Just one's negated and one's not. So it's the same line. So just literally one's on top of the other one. This middle example here, notice when you multiply the top equation by 2, the x's drop out, the y's drop out, but then you have this 36. So when does 0 equal 36? Never, which means this will never happen, therefore there's no solutions and the lines are parallel. So the big key thing here is understanding what does the algebra tell us about the scenario. And then the last example here is, we multiply by 2 and we simply get a solvable answer for 1 point, which means, oh, we have intersecting lines and we're definitely going to get one solution. So the key is always, never, and a solution, and understanding what those mean. Same line, parallel lines, or intersecting lines at a point. Okay, so here's the last slide. I want you to try these 4 examples. Again, pick the system solution that works best for you, i.e. substitution, elimination, or feel free to graph it if you want to try that. And again, this should just be a good refresher for what we've learned from before.